In this first part of the video, we will try to understand what blockchains are and why it is difficult to tamper them. Basically, blockchains are tamper-evident and tamper-resistant data structures implemented in a distributed fashion. Let me ask you a question. When you purchase cheese or honey that are labeled as original, what makes you certain about their origin? To be sure, you need a special database where records can be stored. The records can be verified by anyone, but can be changed by none. Blockchain is basically that special database. First, let us discuss hashes. Hashes are functions that take an input of arbitrary length of data, and as an output, it gives a digest of that data of a specific size. A block is made up of the previous digest and information and a digest of the block whose data is as shown in the figure. We say a block is valid if, for example, its digest starts with 4 zeros. Otherwise, it is invalid. A blockchain is a series of blocks that are linked together. Now we will see a reason why blockchains are hard to tamper. Let us consider the transactions as shown in the figure. Suppose we try to change the data in block 1. This will change the digest of the block, which in turn changes the data of the next block, and all the blocks after the block 0 will become invalid. Also, as blockchains are usually distributed, there are multiple copies of a blockchain available all over the internet. This makes it possible to easily detect and reject altered blocks. This is one of the reasons why blockchains are hard to tamper and hence become important where it needs to protect the integrity of an information. Blockchains find applications in cryptocurrencies like Bitcoin, securely sharing of medical data, tamper-resistant voting mechanisms, and many more. There are other interesting topics related to blockchains. You are highly encouraged to read about them from good sources. Thank you.
This section explains the technique called differential privacy. Have you thought about how your data is protected by tech companies without a breach of privacy? Or how do these tech companies ensure that an untrusted employee does not get access to the data of their customers? Before differential privacy, tech companies anonymize data sets of their customers, but research has shown that such anonymization leads to re-identification attack. A better technique is to randomize the data sets. For instance, a survey tried to record the number of participants who smoke. However, to protect the responses of the participants, they were told to toss a coin. If it outputs head, then they should tell the truth. If tail, they should toss a second coin and respond yes if head and no if tail. This randomization is applicable in differential privacy, which guarantees that two databases that differ in only one record generate identical probability distributions when queried by a private mechanism. By contradiction, if two databases A and B with 100 rows of information and 99 rows of information respectively are queried by a private mechanism, then if they output different results, it becomes possible to know what the missing row would output. Thus, the missing row leaks information and is not differentially private. The monograph showed the formal definition of differential privacy in definition 2.4 proposed by Cynthia Dwork. Differential privacy is secured against post-processing. This means that the output of a differentially private algorithm remains differentially private, even if manipulated by an untrusted data analyst. With differential privacy, tech companies are succeeded in protecting the data of their customers against re-identification and linkage attacks. For more information, please read the monographs. Thank you.